Tonight we're going to go over some of the basics of how we calculate gear distances and belt distances, and then also how we do some amount of ratio calculations as well. Some of it is how we like kind of ballpark it in intuition. Some of it is the actual like math, and we'll show how the calculators work when we like double check our like estimates of where we think we are. It's also why we try to build in a good amount of adjustment into a lot of the systems that we're designing, so that if we're a little off, we can tweak them normally at least a little bit. Okay, so some quick basics. Gears are pretty straightforward. When we're doing gear distance calculations, if we have to custom make our own gearbox, or if we just need like a single reduction somewhere, if we're doing gears, we have to do it quite a bit when we're doing like the absolute encoders this year for the arm, and for the wrist, we're gonna have the gears there. There's a custom gearbox for the twist that will have gears built into it. We don't always do it this way. We like the adjustability of the max planetaries. We like how fast it is. They're very compact. There's a little bit of a weight hit, but after some amount of reduction, they get to be about the same amount of weight. And it's also just faster to produce, faster to have spares, and all of that. So a lot of times, if we can use a max planetary, we will. If there is some reason where we need to not, if the packaging doesn't work, or some other reason, we will do our own for some of the higher torque mechanisms. We'll make our own gearbox. For a lot of the things that if they're going to spin really fast, so any type of roller, we're just going to do that with belts and pulleys, because that can be the lightest solution most of the time. And we'll talk about how we calculate those distances in a second. So for gears, the main thing you basically have to know is the gear pitch. The vast majority of FRC gears that we'll ever see just out, if you go into our bin that's labeled gears, almost all of them are 20 DP gears. This has been the standard size FRC gear for years. I don't exactly know why or when it started. Like COTS parts didn't exist for a long time, but at some point, the like original kit chassis I think had metric gears, and then eventually they swapped over to 20 DP in one of those years, sometime in like I'm guessing like 2006, 7, like a long time ago. And then all of the gears sold in FRC for a while were just sold at this 20 DP size. Every once in a while you'll see tinier teeth, so you'll see smaller teeth. Those are either, sometimes there's some weird metric thing from like a long time ago, or they're 32 DP. Those used to be really popular when we had really small motors, and we just needed to have a really small gear at the end of that motor and needed a little bit more teeth. And so we would use 32 DP gears to do that, but they were really easy to break, even in steel. You could break the teeth on those if you had them in any sort of like heavy load application, so we don't use those. And then the other ones we'll see sometimes are 10 DP gears, which basically the gear tooth at that point is twice as big as the ones for 20. And so the pitch is basically just how big the gear tooth is. And so for 10 DP, we use those on things that just need to be much larger. So like last year we used it on the pivot. So we can like laser cut 10 DP. You can like CNC route the gear teeth on 10 DP, where because of how tiny these gears are, it's really hard to like cut these with a router because you can't really get the bit inside that groove. You'd have to have a really small bit. 10 DP makes that easier. The other reason we use 10 DP is for all of our 3D printed gears, just because the gear teeth are bigger and they're harder to break the plastic. They have more material behind each one, and so that works really well. So when we're talking about gear pitch, the equation is really simple for gears because it's a standard pitch that we're using. In our standard measurements, we can get the diameter that we need to be able to like do the gear distances and things without even really using a calculator, because all it is just teeth over pitch. So if you know how many gear teeth a gear has, you can divide it by the pitch, and then you can get the pitch diameter. And for gears, all you have to do is make sure those two pitch diameters are tangent, and you're good to run that gearbox. So we don't have to add anything. There's sometimes people like add a little bit of distance to make sure they don't mess right. With modern FRC gears, you pretty much don't have to do that. Most of it works pretty okay right on. There were some people who would add like 0.003 or something. You could add like 3 thou or something very small to make it mesh a little bit looser, in case you didn't want it to like touch as hard, right? Like this gear would be a little bit further away than this one. So if we're looking at this sketch here, we can see on this gear, so this is a 20 DP gear, and this is a 20 tooth gear. So it has a 1-inch pitch diameter. So that's our pitch diameter here, and that's what we care about in the sketch for when we're going to actually mesh them together. So that's what we care about for our distance between this gear and another gear, is that these two circles line up. So if we were meshing this to a 40 tooth gear, we'd have a 2-inch circle out here, and we'd make sure that those two circles are tangent to each other. And that gives us a center distance of 1.5 inches, because it's half of this gear's diameter and then half of this gear's diameter gives us our center distance. So it's relatively easy, especially in CAD, to build up some pretty complicated gear trains, because all you're really doing is connecting circles tangent to each other. So if we wanted to have like a second reduction out over here, we could have another gear, maybe it's the same size, we could have another 20 tooth gear, we could make those equal to each other, and we could come out over here, we could make these two tangent, we could make these two equal, and now we know if we put our bearings in these 3 spots, we could have a 20 tooth connected to a 40 tooth. In front of or behind that, we could have another 20 tooth connected to a 40 tooth, and you could just keep going for as long as you wanted. Because these are, it's just tangent, how you can make them more compact is you could have like the gearbox maybe up here somewhere. So as long as it's not hitting this shaft or bearing, you could like make it more compact, and you could still have the output of the gearbox somewhere up here. So it just kind of depends on how we're trying to like package it all together. But all they really have to do is be tangent to each other. Inside of the Origin Cube feature script, so when we add the Origin Cube into our part studio, frcdesign.org added in the functions and variables, and so with those, we're able to get some nice little functions around. Oh, it lost its mate connector in the transform. Oops. For some reason, I'm not entirely sure why. Let me delete that. Okay, the gear's back. Cool. Okay, so in this sketch, if you want to know the actual outside diameter of the gear, we're able to just have the pitch here, and then they have a variable where you can just do the pound sign, and it brings up the whole list of the different variables, so we don't have to go find a calculator or find some reference to know any of this. And we can know that the offset from the pitch diameter to the true diameter of the gear, the OD, the outside diameter of the gear, is 0.05, and so we can just click that in there, and now we can have that outside diameter too, because this is important if we want to make sure a shaft isn't hitting this, or another gear isn't hitting this. Depending on what we're doing, we want to make sure nothing's going to contact that. So when we're sketching, having the actual pitch diameter and the outside diameter is pretty helpful. We didn't talk too much about the ratios. There's a whole slide on the full, there's a whole like training slides and video on the full mechanical advantage of stuff of like how, why we have the gears and what we do with them. We're not going to cover all that tonight. It could be its own like hour presentation. The basics of it is that it's just ratios. We can divide the output over the input. So in like this picture, it's 48 over 16 equals 3. In our example, it's 40 over 20 equals 2. And so this would be a 2-to-1 reduction, because for every 1 time, or every 2 times that this 10-tooth or this 20-tooth gear spins, this 40-tooth gear spins once, because it's still only moving 1 gear tooth at a time as they're pushing against each other. And so we can just divide this size over this one to get our gear ratios. And so this means this is spinning at half the speed of this shaft here. It also means that it's going to be spinning with double the torque. Torque is, for most cases, you can just think of it as rotational force. And so that's going to double our force. So if we need to, the motor is spinning super, super fast, and we need to have that motor do something that requires a lot of energy and a lot of force, like climbing, for example, we're going to have a lot of reduction from the motor to the output so that we can use all of that torque in a very usable manner and actually do whatever the task we're trying to do. So we'll look at like how we actually calculate some of those ratios in a little bit. But let's talk about belts quickly here for a second. Okay, so belts are a little bit weird, mostly because pretty much most of the standards that timing belts use in the world are metric. Like there are some that are built on inch systems, but it's really not worth converting all that much. Like most of like the different timing belts that exist in like standard industry largely are metric. Rev has a belt that is 1/4 inch pitch, and so they have belts and pulleys for that. But they're the only company you can buy those belts and pulleys from, so it gets a little bit weird in trying to find the exact belt length and things that you need. You have so much of a limited supply, where for the standard belts and pulleys that we use, the metric ones, we're able to buy those from all the standard industrial belt suppliers, and in basically any length that we could ever imagine, and get them very fast and not really have to worry about them being out of stock, because if one place is, we can go to some other place. They're very cheap because just a lot of industries use them for a lot of different things, so they can be relatively inexpensive for us. We can stock a whole lot of them, so we have like back in the closet on the belt wall, we have nearly every size belt we'd want for any of the smaller sizes, and so it works out pretty well to use these kind of standard sizes. These were brought in. These were kind of brought in specifically to FRC in a couple different ways. So Vex started making pulleys and things at one point with the Vex Pro line. The Kitbot has been Gates donation specific pulleys and belts for a while as well. And so there are a couple different sizes that have been used at different points. But for the most part, these have kind of become our standard and a lot of other teams' standard for what to use. So we largely only use 5mm, HTD, 9mm, or 15mm. That's very confusing because there's two different numbers in here, and you have to know that one of them means one thing and the other ones mean a different thing, and you kind of just have to know that. So the 5mm at the front is what we're talking about here, is what we're talking about belt pitch. So that's often abbreviated just as 5M. It'll have a single M there because that tells you not only the pitch sometimes, but it'll also tell you the profile. So there's a lot of different belts, like infinite different types of belts that probably exist. There are just pure flat belts, there are round belts, there are trapezoidal belts, so instead of having little like what look kind of like semicircles, they have just pure trapezoids. There's ones that are fully semicircle, like if you look exactly here, they have a little bit of a flat on this picture. HTD is pretty much semicircular. They have a little bit of, the geometry is not exactly a semicircle, it kind of flattens out as it goes into the belt itself. But it's a pretty common standard belt across industries, so we can buy these same type of belts are run like on 3D printers, or like for this big would be on like some very large 3D printers if it was as big of pitch that we're using. But they're also used in like laser cutters or CNC machines. They're used in a lot of places to do a lot of the same things we do with them. Move things back and forth, spin things, whatever they need to do. So for us, HTD sets the profile that we're using. There's some complicated stuff where you can use some specific types of other pulleys that aren't exactly HDD, or some specific types of belts, and interchange them. For the most part, you don't need to get into that very often. Most of our suppliers are all kind of standardizing on the same belts and pulleys, and they kind of all work together for the most part. Similar to gears, the 5mm is the belt pitch, and so that's basically just the distance between each tooth, or like the center of each tooth. So if you got a smaller pitch, you'd have much smaller teeth. If you had a bigger pitch, you'd have much bigger teeth. 5mm seems to work well in our applications. We can have a relatively small pulley on the motor side, normally like a 12-tooth pulley on our motor, going to a larger pulley out wherever we need to use it. A lot of times that ends up being like 18 or 24 or something. So we can get a 1.5 to 1 or a 2 to 1 reduction from the motor to whatever we're spinning. Or we can go up more, or we can have a gear afterwards, or whatever you need to do to kind of get the motion and profile that you want from the motor to whatever you're actually turning at the end of it. The other part of the belt that you have to specify is how wide the belt is. And so for the most part, the pulleys that we use in FRC allow us to either use a 9mm belt or a 15mm belt. This standard was kind of set by VexPro when they introduced their belt system and the products for it. And the way they set it up is that they sold some 9mm pulleys that are slightly bigger than 9, so the belt has a little bit of room to play. And then they also sold pulleys that were said to be for 15mm, but they actually had enough room for 2 9mm wide belts. So, those pulleys were a little bit bigger than 18mm, and so it allowed a single pulley to be run on, to have 2 belts run on it, so you could connect them together and things. And so that's one of the reasons that we still do that today, is we'll still make pulleys, even if we're 3D printing them or however we're making them, that are a little bit wider. We'll make them about 20mm wide sometimes to make sure that we can fit the belts. For the most part, you don't have to worry too much about specific widths. Like, you can run a 9mm belt on a much wider pulley and it works fine. The thing that you really do have to worry about when you're making belts work is you have to have their center distances correctly. So just like gears, they have a pitch diameter. And so that pitch diameter is what we're worried about when we're figuring out the center distance. But it gets a little bit more complicated with belts and pulleys because they're not just touching each other. You have to actually run a belt around both pulleys. So what we're trying to do is find our center to center distance, right? So the center between pulley 1 and the center of pulley 2 for some specific belt length that we want. I didn't put this on the slides, but we'll talk about it for a bit. Belts are specified in 2 different ways. They also have to have the pitch and the belt type and the width. But then to actually say how big the belt is, you have to either say how many teeth the belt has, or you have to say its actual pitch diameter, pitch circumference of the belt. So like how long the belt actually is going all the way around. Either of those numbers works. You can calculate pitch circumference from number of teeth as long as you know the pitch. So that's totally fine. A lot of times we'll use belt teeth a lot easier in our vocabulary when we're talking about things. We'll talk about a 60-tooth belt or a 65-tooth belt, which works well for most of like FRC applications, and a lot of the FRC vendors sell them that way. Most of the industry, if you go and work somewhere, if you're trying to buy from like a non-specific robot supplier, they're going to do it on their circumference of the belt and not on the teeth. So you actually have to like do the math to figure out the teeth versus circumference, to make sure you're getting the belt that you actually want. When we're actually trying to figure out our center to center distance so we can calculate the belt we need, the diameters matter a lot here because they're not just being tangent. You have to do basically all the trig. If we didn't have calculators, we'd have to do all the trig to figure out what the circumferences actually are if you have a line running tangent between these two circles and what part of this circumference of the circle is still there. And so there is some math behind it. It's not terrible math. You can definitely do it if you've gone through geometry, maybe a little bit of pre-calc to do some of the trig. It's not that hard, but luckily we just don't have to do it. We have calculators that do it for us. So for two pulleys that we're just doing straight across and the belt's just connecting them, we just use distance calculators. If we have to make a more complex belt path, which we've had to do a couple times on this robot, so if we have like an idler somewhere, so if we need the belt to like run down around something else and then over to here, we don't have the luxury of just using a belt calculator for that. So then we can basically do it geometrically in CAD, and we can like draw it out and sketch it and calculate how long of a belt we need, and then we can kind of define that all and get it in a position so that our system will work. So that's what we were just having to do with the corral team, because we needed to go around an idler to make sure the belt wasn't hitting the coral. And so we had to do a little bit more complicated of a belt path to figure out and make sure we can make that mechanism run with the belt we want to, and see how to make that work. We also had to do it with the elevator, since we were going over all of the different idler pulleys that are just redirecting the belt's path around so it can actually work as the elevator. So we had to sketch all of that to make sure the belt path was very good. We didn't have to know its exact distance, because in that case the belt isn't continuous. It's not like a full loop. We tie off the two ends at different points. But for the corral, we did. So we did have to know exactly what that distance was. And even as we were doing it, we kind of like messed up a little bit. Then we figured it out before we actually cut anything, luckily. And then we think it's going to work when we actually put it together tomorrow. Okay, so let's look at belts real fast. So for a specific pulley, the nice thing that we have now is we can do it built in to Onshape. Actually, let's do it on Recalc first, because we can look at all the numbers a little quicker. So Recalc is a nice website built by Justin Turvey. He's up in New England, and so he does most of the code for this. But it's basically just designed to be a nice web calculator for a lot of the different things you might need to do on a FRC robot. There's a bunch of little like information and stuff down here. It's just a nice site to go and learn. But a lot of times we're using the belt calculator or the linear mechanism calculator or arm calculator, and those are kind of how we can pick our gear ratios and things. And then also for belts, just getting our distances right. So with the belt calculator, it does look a little intimidating. There's a lot of numbers. With all of Recalc, any of the gray boxes you're not typing in. That's just going to be stuff it gives you as output. So you're only filling in the white boxes. Everything over here is just links to help you buy the belts you need, or the pulleys you need. So for most of our stuff, the first thing we do when we open the belt calculator is we swap this pitch to 5. And so it's 5 millimeter. And then a lot of times we'll have some mechanism that we're trying to build. Like if we have a motor here and we're trying to run a roller over here, we would need to know, okay, this is about 4 inches that we're trying to get this to be. So we'll sketch it sometimes with just, whatever units we need to make it kind of look right. And then we'll come into the calculator and we can tell it, okay, we want it to be about 4 inches. We don't need any extra center distance or anything, and we don't know what belt we want yet. We know that the motor is going to have like a 12-tooth pulley. We can say the roller is going to have a 24-tooth pulley. And if we do that, we can see our options are either a 55-tooth belt with a 3.6222 center distance, or we can run a 60-tooth belt with a 4.1167 center distance. You can tell it different tooth increments. For the most part, 5 is pretty good. For 5 teeth increments and a 5 millimeter pitch, that means we're changing 25 millimeter of our belt circumference each time, which is about an inch. And that ends up working out pretty well. We're able to stock all of the lengths pretty nicely. So in here, the 60 tooth belt times 5 is a 300, I believe, right? So if we come down here and we look at that 60 tooth at V-Belt Guys, this is one of the places that we've found that we really like to buy belts from. And so this is a 300 long belt, so that means it's 300 millimeters in circumference. It's 5M, so it's 5 millimeter pitch, HTD in this case. We know that that's true because that's just how they like spec it. And then the 09 is for 9 millimeters wide. And so you don't always have to like know this. Sometimes I'll have to go in here and like search for something if I'm not sure they sell it. But you can also just do it on Recalc and it'll give you the links because he built it all to be able to link specifically to these different vendors. And so we can buy whatever belts we need. And like I said, a lot of these belts are super cheap. This is a $2.60 belt. That's why we can stock whatever, 15 of them over in the closet and not worry about it. Okay, the other way to do this, so if we don't want to use Recalc and we just want to do it directly in Onshape, is because of that origin cube functions that we have, we can go ahead and just type it into here. So if we do, if we start typing belt, we can choose belt 5 millimeter. We can tell it our belt teeth, I believe is what it takes. So we can type in like 60. Then we can type in one of the first pulley diameters. So in this case, we're gonna have a 12 over here. And then we can type in 24. And then if we hit enter, it gives us that 4.117, which is basically the same thing that Recalc gave us as well. And so that makes it really fast and easy to do some belt calculations. If we're not sure what we're going into, you can go in and be like, okay, maybe I want it 65. Or you can just literally just be typing in and finding the value here without ever having to actually go to some other calculator. You could just find a belt that works. This also works well if you're just trying to find one that we already have in our closet, and just figuring out where you might have to put the motor to get the roller to work the way we want. Yeah, and then I don't remember if this had pulleys. Yeah, so it does. It has pitch diameters for pulleys too, so you can come in here and just say, okay, I want, it's a 5 millimeter, this one's gonna be the 24. And so it'll give me the pitch diameter for that pulley, and I can do the same thing here as well and make that 12. And so now I have the pitch diameters of both those pulleys on a 60 tooth belt distance, and this is pretty close to exactly what we would actually want on our robot. For CAD, the other thing that we were able to do is we can insert the pulleys in the assembly the normal way, or we can create them if we're like CADing them, building them into something, and we're going to print them. We can do that. Then we can also generate the belt. So there's a few different feature scripts for it. Contactless belt works pretty well. It's one of Julia's. She did a ton of really good feature scripts for FRC. And so this is the normal one we use if we're just trying to get a quick belt. And so we can basically tell it, okay, we want our 12 tooth pulley at the front. We want our 24 tooth pulley on the other side. And then we can do it in place. So we can tell it, okay, I just want to go from this point to this point, and it'll make our belt for us. We can also tell it the width of the belt. So say maybe we only want it to be 9 millimeter. It knows that it's already 5 millimeter pitch. We don't necessarily have to have an offset. We can get rid of that. And then you can set the belt thickness as well if we calculate that differently somehow. We can decide how we want to calculate that. Most of the time, this is pretty close. And so this belt lets us have a nice, simple belt that doesn't take a lot of time to load. We're not trying to like have each of the teeth actually in there. There are other feature scripts that'll do that. If we actually want all of the teeth for some reason, we could do it. But for the most part in ARCAD, this is all we care about. This lets us see if the belt's going to run into anything. It lets us see if we're going to hit anything or if the belt path looks clean and good. And like I said, there are several others that you can go through and make much more complicated belts if we need to, that are totally doable and work well. For the most part, this one is just fast and lightweight and simple and lets us make the belts pretty easily. And then you can do these, if you do them in place in the part studio, they insert nicely into the assembly, like right where they're supposed to be. Sometimes if you have to do them in a different part studio or something, you'll have to like rotate them when you go to mate them, which can be a little weird if you don't get the angles right. But as long as they're close, they're pretty good for ARCAD. We're not super worried if this is not exactly concentric to the other pulley. As long as it looks about right, we're pretty happy. Okay, any questions on gear distances or what we use for belts or how the formulas work or anything like that? Okay. Let's talk about, I'm going to do like, how much time do we have? I'm going to do like 10 minutes on our gear ratio stuff. So, for most of the robot, we can kind of divide things into either high speed applications or high torque applications. There's some times where there's like a mixture of both that we need. But largely you're kind of in those two areas for the most part. So like we can imagine on this robot that we are currently designing, the rollers are going to be very high speed applications. We want those spinning very fast. The arms, elevator, climber, all of those are going to be relatively high torque applications. We don't actually want these spinning very fast in terms of revolutions, right? It would be very bad if our shoulder started spinning at 2,000 RPM. That would be very, very bad. That would break lots of things. We do not want that. However, if our coral roller was spinning at 2,000 RPM, that might be fine. We want these wheels spinning very, very fast. And so that helps us actually intake the coral, and they don't have to exert a ton of force on anything. They're not trying to lift anything. They just need to be able to suck in the coral, and as long as they can do that, that's all we care about. So when we're looking at gear ratios, we get a little bit, some of it's a little fuzzy. We don't often go through and try to fully optimize every single one just because it takes some amount of time. And for the most part, as long as we're in the ballpark, the motors that we're using now and the software control and things that we have allow us to basically, if we're close, the performance difference for like optimizing even more isn't really there for the amount of time it takes and for how much we have to know ahead of time to be able to even do that. So for some of it, we'll do things like in here where we have the max planetaries. We planned for 2 stages here with a, I believe that's 14 to 72 up on the arm. And so if we can do that calculation real fast, we can go over to recalc. I don't know if it actually does. It'll only let you type the ratio. So when we're typing the ratios up, we can just use like Google or whatever to figure out the math. But 72 over 14 is about 5 to 1. So we're getting a 5 to 1 reduction from the chain on this end. If we have 2 max planetary slices here, that means we can, any of those, the max planetary, any one of the slices can be anywhere from a 3, a 4, a 5, or a 9. And so we basically just multiply all of those numbers together. So we could do a 3, 3, and a 5. And so that would be 3 times 3 times 5. And it's roughly 45 to 1. If we make one of these other ones a 5, we can get up to 75 to 1. If we wanted to get really crazy, we could do like 9. We can do like 225 to 1. So we have a lot of room to play if we need to. For the arm calculator here, if we have one Kraken powering it, and we're at, let's say, like that 75 number is real, that's probably pretty close. That's a rough guess of where we might be. If our arm mass is like, let's say it's even a heavy, because we can error on the side of heavy here. We can give it a little bit more current if we need to. And our center of mass distance is probably not actually 20, it's probably closer to like 10 for the shoulder joint. So if we look at the shoulder, it's moving most of its mass out here, which is going to be a little over 10 when it's this way, a little more plus the actual length out there. So it's very likely the shoulder will be geared higher than the elbow since it's moving more mass. So you might want to move that up. We could do, instead of 355, maybe we do 455. We go all the way to 100. And if our center of mass distance, we can error pretty far. We can say it's all the way at 20. I don't think it will be. It's definitely not going to be 20 pounds. But even if it was, in this case, if we had 100 to 1 gear reduction and it was 20 pounds, we could move the arm 90 degrees in half a second, according to this calculator. That's a lot of times about what our goal is for a lot of our movements, is to make sure we can do it in half a second. 180 would be all the way from full down to full up in a little over half a second, which would still work if we needed it to. And these are very gross, like overestimates of where we think how much the arm will actually weigh and how far away we think the actual center of mass would be for the most part. But even if these were accurate, or if they're a little bit off in the other way, we could then go and change our reduction and still get a little bit faster or leaner if we need to. So if we decided, oh wait, no, we actually wanted a little bit more reduction, we wanted to be at like 125, we could, and we could see that makes it, that actually doesn't change that much for our speed there. So that's still like 640, so that means we're probably over geared here. So if we drop this down, if we try to get somewhere in like an 80, that's pretty close. Okay, so we're somewhere, yeah, somewhere in there is about right, because as you go up, it'll start getting slower, it'll start getting faster, and you can find about where this balances out. And that's normally pretty close to what our estimate is going to be. We can decide to make these estimates a little bit closer to real life as we know more, as we like know exactly how much the arm's going to weigh, or whatever the motion of the robot is going to do. We'll get these a little bit closer and make sure we're about right. So we did this when we're like calculating the twist, for example. In this gearbox, this is all fake right now, but there will be gears here, and we were looking at like, okay, how much gear reduction do we think we actually need? We did a little bit more approximation to be like, okay, if this is, we know the coral is going to be sitting like 6.5 inches out here. So if we put all of that at 6.5, what does that look like if we have 10 pounds out at that number? How much force does it take to rotate it? How fast can we spin the wrist? And I think when we did it for what we're doing, we could do like a full 360 in like somewhere around half a second or like 0.6 seconds or something, which we should never need to do a full 360 with the wrist. But it should be plenty fast for what we're doing at a pretty moderate, I think it's somewhere around like 20 to 1 if I remember correctly. We have it all documented somewhere. But it gets something like that, gets us in the ballpark of where we want to be for the mechanisms. And then for the worst case, for a lot of these, we know if we have to, we can swap them or change them to actually improve as well if we need to later on. But we try to get it pretty close to accurate, or where we at least think the system will work when we're building it the first time, at least pretty close. Okay, let's talk about the part sheet. Okay, so this document, Gamma Ray 2025 robot sheet, lets us basically have a somewhat of a standard naming system, but more importantly, it lets us actually see all of the stuff that we have to make. So this sheet gets very long. There are a lot of parts. This is every part, so there's lots of little shafts. This is a big chunk of the robot is the elevator and the shoulder joint and everything. So that's why there's like 75 parts here. It's a big amount of the robot ends up being this part of the robot. And so they've gone through and we like kind of know what all these parts are. They have names, and it works out. Most of the other subsystems haven't finalized what's going actually on the robot. Drivetrain has, and it needs to get its parts in here and renamed and on shape so that we can track them correctly. But most everything else doesn't have this fully set up yet because we don't know exactly that those parts are actually going to go on robot. A lot of them are still just kind of SketchUps and test versions, and then we'll go back in and rename everything, give it part numbers, basically when we're ready to actually manufacture. So a lot of these will get changed here shortly to ready for manufacture, and so we can swap down and like see how we're ready to do things, or like design and review, so we can go and check. Some of these we don't use specifically all that much about certain parts of the robot. Like a lot of times these will be communicated through Slack and things, so we don't always use these boxes. But the main thing we want to communicate is whether we're ready to actually build it. So if it's on ready to manufacture, or if it's like ready for outsource, especially if we have to send it off to one of our sheet metal sponsors, we want to make sure that list is good so that when I need to go and figure out what gets sent off at that time, we know what is ready for outsource, and then I can also label it outsource ordered so you all know parts are going to be coming in at some point once those are ready. The other part of it is ready for finishing, which is when we have the parts ready to actually be powder coated. And then our the things that happen after that too. So like if we've cut all the shafts and lathed them or something, but now we have the bunch of them, but they're untapped still. We can have them ready for tapping, so people can take them to the tapping station and do the tapped holes on them. Same with like deburring any of the parts before powder coat possibly. For bending, if they have to go into the sheet metal press or the sheet metal press brake, anything like that can be documented here, and so we kind of know what's the next step to get these parts ready. We have a status for the PM parts because we'll build the practice machine first. For the most part, at least those mechanisms will be built first. Like we don't expect everything to be fully functioning on practice before we get at least started on FM, but at least some parts of it will. So like the full drivetrain of PM will be assembled. We'll make sure everything's fitting together nicely. Same with like the elevator and everything. And then if we're pretty happy with it, then we'll build all the parts for FM after we've done some amount of testing, some amount of at least making sure things fit well, even if it's not fully powered on and driving yet, for some of it. And then for other parts of it, we won't build the FM version until we're absolutely sure the PM one is ready and we're not doing any more iteration on it. So like a lot of the certain parts of the robot we know we can iterate more often. The drivetrain and the elevator aren't one of them. So those are the ones that we focus the most on getting ready to be fully produced because we need to not really change those very much. So once they're kind of test fit and we know they kind of work, we'll build the FM version, and hopefully we're not replacing those throughout the season. If, say, the algae intake or climber or corral mech needs to get replaced, that's very likely going to happen. Like we're going to make design improvements, we're going to make design changes, make it more robust, make everything faster, make it work better. So we expect to be replacing those pretty regularly. So we'll build the PM version and then like fully test it, figure out how it works, and then we'll probably rev it again, make a new one, test that one, and then decide, okay, this is the one that we're taking to our first competition, and then we'll build the FM version and the spare parts for it, so that we know we're good to go for our competitions. for things kind of at the end of their respective chain of parts or mechanisms. So yeah, so when the mechanism groups are ready to make a part, you can go in and basically choose which assembly you have. You can name it, kind of describe what that part is going to do. Middle corral plate, whatever it is. You can choose who designed it. You can choose what material it's going to be made out of. If something's not on here or something, let us know. We can add things. You can choose how it's going to be made, if it's going to be finished, how many per robot. And then when you're finished, it gives you a part name here. So I'll normally copy this and go, I'll Control-C this, click Add to Part, and then go rename it in Onshape with this name. And then once you click here, it'll run the script, and that'll get added down in here. And so it gets added to the list, and it gets the next number ready for this assembly. So this works very well for us. I'm going to go ahead and delete that so it's not actually on the part list until one of the people in Corral goes and actually does it. But so this is kind of the way that we want every part of the robot. So anything that has to get manufactured, right? We don't do it for every single bolt unless the bolt has to get modified in some way. But for any custom part that goes on the robot, if it's something that has to be cut to length, something that has to be laser cut, water jet, tap, drilled, whatever, should have a part number and part name. And so this is what goes in to Onshape. This also lets us search up things pretty easy on Onshape. It lets us version some things nicely if we need to. We don't currently have a way to version in here. That's one of the things we might look at adding this year, is as we update stuff, figuring out a way to either like, do we fully rename it and give it a new number, or do we have ways to give it a version number or a version date or something like that? Because we had a little bit of issues as we were iterating so fast last year where we had different parts on practice and comp, making sure that we kind of know where those are. We'll be using branches in Onshape more. We already have been through the prototyping process, and that's been working pretty nicely. But we do want to figure out and make sure that we know which parts we have, which spares we have, because if we're iterating things and say we change the algae intake, but then we don't actually change the spares, if we break it at competition, we want to make sure we're putting on the good version, if at all possible. So we want to make sure we have the right spares of each different part, and we're not going to try to have to like cobble things together, mix matching versions of different parts together at events if we need to. Most of the things we do on the sheet are just in part generator and parts list. Most of the other stuff is just here to do a little bit of referencing and things. We'll do like inventory at some point, make sure we have stuff. This is where we can add names and things. If we have more people doing designing or whatever, we can add names in here. COTS parts, if there's specific things we need in the assembly, getting inventories for your subsystem is very useful. So if there's some part that you know you're going to need quantity of, especially if there's anything that we start having as wear items at all, so if something that we know is going to be swapped regularly all season, if something is just running down, whatever it is where it might have to be regularly maintenanced and regularly exchanged or swapped in, knowing how many we have all the time is very helpful. We do some of this in like the purchase channel in Slack, but others just making sure that we have what we need to actually build the robots, have spares, and be able to compete at a high level is what we're trying to do. Okay, I think that's most of it. All right, I think that's all I have.